Hello and welcome to lecture 16 of the course Computational Complexity. In this lecture, we will see Savitch's theorem. Okay, this was discovered by or proved by Walter Savitch in 1970. Right. In this theorem, we see a relation between what is achievable in non-deterministic space-bounded machine and what is achievable in deterministic space-bounded machine. Okay. So in very simple terms, what it says is that if there is a non-deterministic space-bounded machine whose space usage is Fn, then there is an equivalent deterministic space-bounded machine whose space usage is Fn squared, right? So if there is an n-space machine which runs in n squared space, then there is an equivalent d-space machine which runs in at most n power 4 space. Okay, so you can go from a non-deterministic space-bounded machine to a deterministic space-bounded machine, right, by just squaring the space required, right. So you can give up non-determinism in exchange for square the amount of space that is required, right. And like I said in one of the previous lectures, we have this requirement that Fn we always assume to be at least log n. So it's a bit of a surprising thing, right, because we saw that if a language is in NP such as SAT, right, we don't know whether it is in P. So we know that SAT is in probably some NP, non-deterministic polynomial time, and there is nothing like you can square the time required and get a deterministic machine for that, because a square of a polynomial is still a polynomial. But in the case of space, if a language can be decided in non-deterministic polynomial space or non-deterministic space Fn, then it can be decided in deterministic space Fn squared, right. So that in that sense it's a bit of a surprise, right. So this is one place where we see the differences between non-deterministic, between space-bounded complexity and time-bounded complexity, right. So just to write it informally, if we can square the space usage, right, then we can give up the non-determinism. So basically you can trade non-determinism by using extra space like squared mini space, right. So now let us see how to this is very interesting, because we are giving up non-determinism in exchange for a bit more space, and we do not have anything like this in the case of time complexity. So let us see how to prove it, and the proof turns out to be surprisingly simple, right. So suppose there is a non-deterministic Turing machine, or suppose there is a language that is decidable by a non-deterministic Turing machine, right. And we already saw that to simulate this non-deterministic Turing machine, all we need to do is check whether there is a path from the starting configuration to the accepting configuration, right. So I just write that down. As we saw in previous lectures, at least 2 lectures we saw this, right. Simulating a space-bounded Turing machine or a non-deterministic Turing machine is accomplished, so it can be accomplished by searching for a path from C start, which is a notation for starting configuration, to C accept, which is the accepting configuration in the configuration graph. So, and we also saw in the previous lecture that given a non-deterministic Turing machine, we can modify it in such a way that there is a unique accepting configuration. So in the configuration graph, all we have to do is search whether there is a path from the C start to the C accept, right? So so suppose A is a language, that is a non-deterministic space Fn. Now that means there is a non-deterministic Turing machine N, right? So let us call it N. Let that be the non-deterministic Turing machine that runs in order Fn space and decides A, right? Now how many, again this is something that we have already seen, how many configurations can N possibly have? Again, this calculation we performed already in one of the previous lectures. N can have, I think, 2 of the previous lectures. N can have at most 2 power order Fn configurations, okay? So instead of working with an asymptotic and abstract order Fn, let us fix the constant involved in this order Fn. Let us call it d times Fn, where d is some constant. Now we need to decide. So in calculations, it's sometimes helpful to actually work with exact constants instead of the O notation, because sometimes it is risky to work with the O notation, because you don't, sometimes it's possible to lose track of the way the order notation explodes. So that is why, to be extra careful, we use the exact constant here. So we'll just call it dfn, right? Now we need to decide if there is a path from C start to C accept, okay? But instead what we will do is, we know that there are at most 2 power dfn configurations, at most 2 power dfn configurations. So we'll just check whether there is a path of this length, because if there is a path of length longer than this, that means that path revisits some vertex. So it can happen something like this. So let's say this is C start. Now if there is a path of longer length, it means it may go something like this, something like this, something like this, something like this. So some looping happens and finally it goes to C accept. So which means actually there is a shorter path, right? You could have gone like this and then like this, right? You don't need to actually go through the loop. So whenever there is a path in this graph, because this graph has at most 2 power dfn vertices, there is a path that if there is a path, then there is a path of at most 2 power dfn vertices. You can remove all these loops that arise. So perhaps there are loops at multiple locations, perhaps there is a big loop here also, but you can ignore all that. You can ignore all that and get a simple path of at most 2 power dfn vertices, right? Now again, we named this problem of finding whether there is a path from a vertex S to a vertex T in a directed graph as the path problem, right? So now we will run a we'll make a function call, okay, and here this path v1 v2 t stands or is a program or is a pseudocode that will tell whether there is a path from v1 to v2 using at most t vertices or at most t steps. Okay, this is what we are trying to do with this subroutine or with this pseudocode. And the reason we named it like this is that we can make recursive calls. So I will use this recursively. That's why I called it path v1 v2 t. This is asking whether there is a path of length at most t from v1 to v2. So when t is equal to 1, we just are checking whether the v1 to v2 is a edge, or v1 to v2 can also be the same vertex. So if t equal to 1, we just decide, it is a base case, is v1 equal to v2 or is v1 to v2 an edge. If it is not the case, what we do is we check for all the vertices w, right? So if there is a path of length at most t, that means there is a middle vertex. So let's say the middle vertex was some vertex called w. v1 to w should be a path of length at most t by 2, and w to v2, right? So there's a figure here. If there is a path from v1 to v2, then there is a midpoint, right? So let's call that midpoint w. So then v1 to w is of length at most t divided by 2, and w to v2 is also of length at most t divided by 2. So now what is the midpoint w? We do not know. So to figure that out, what we do is we just try out all possible w's, right? So remember, we are in the space bounded setting and we are trying to get a deterministic space bounded machine. So we just try out all possible w's and call the function path again, call the subroutine path again. So for v1 w t divided by 2 and w v2 t divided by 2, right? So v1 to w is there a path, w to v2 is there a path, and if both of these are there, then you accept. Okay, so notice that if there is a path from v1 to v2 of length at most t, then it has a midpoint w, and there will be a path from v1 to w of at most t by 2 and w to v2 of length at most t divided by 2. So if v1 to v2 there is a path of length t, then both of these should accept. v1 w t by 2 and w v2 t by 2 should accept, and we accept the top level call if both of these accept, and we reject if even one of them, for no w this leads to an accept. If for some w this accepts, then we accept. If for none of the w's this accepts, meaning none of the w can be a midpoint vertex, right? So which means there is no path. If there is a path, then there has to be a midpoint vertex, right? So this is a simple pseudocode using a very simple recursive technique, and somehow this is enough, all that we need to show the Savitch's theorem. So you may be surprised how such a simple idea is leading us to such a powerful theorem statement, right? So again, this is just what I said. There is a path from v1 to v2 using at most t vertices if there is a midpoint vertex w such that v1 to w is t by 2 vertices and w to v2 is at most t by 2 steps, right? So now all that remains is to show the analysis of this, to show that this recursive function call uses at most order fn squared space, right? So what should be t here? T is we are checking whether there is a path from C start to C accept that uses t steps. And what is t here? T should be this number, right? Sorry, t should be this number, 2 power d times fn, which is the number of vertices in the configuration graph. So 2 power dfn vertices is what this graph has, right? Right. So how much space does it take? So let us see what happens when the recursive call is made, right? So at any level of recursive call, you may recall from what you learned in algorithms or data structures that when a recursive call is made, the program needs to store some information in the stack, right? That's how recursive calls are made. And when the recursive call returns the answer, and then it needs to resume the computation from wherever it left off. So it needs to store the state information and then need to resume the computation. So what is the state information that is required here, right? So the state information that is required here is, so at the top level we are making the call for v1, v2 and t, right? So and that when we make this recursive call, we need to, so we will call the function v1 w t by 2, but we need to know where we called it from. So we need to remember v1 v2 t is where we called it from, so we need to remember that. And when from v1 w t by 2, when a further subcall is made, then again v1 w t by 2 will be kept in the stack, and so on. So that many nested calls will be made, and all these values of v1, v2, t of all these nested calls should be stored somewhere in the stack, and this is what we need to store in the stack. So the idea is to measure how much of the stack or how much space is being used for all these things. So let's try to understand. So let's see how many levels of these recursive calls are required, right? So initially at the top level, we need the number of steps that are required, the number of, like, how many we need to check from v1 to v2, there is a path of length at most t. And in the second call, sorry, we are checking whether v1 to w there is a path of length at most t by 2, and over here again w to v2 there is a path of length at most t divided by 2, right, and so on. And then each of these calls make further calls, and where we are checking whether there are paths of length t divided by 4, and further calls are of length t divided by 8. So now how big is this tree, right? Well, at each level the distance between the starting vertex and the destination vertex is becoming half. So how long does it take for t to become a constant, or t to become 1? The answer is simply log t to the base 2, right? So we will need log t levels. I am not sure if I said it before, but I will say it now. Whenever we say log without specifying the base in this course, if the base is not explicitly mentioned, you can assume that the base is 2, okay, and this will be most likely the case for most of the computer science courses, right? We will need log t levels where log is the base 2, okay. The initial call has t equal to 2 power d times fn, right? And for each, so after log t levels, what happens is that then we are just checking whether there is an edge of length 1 or something, which is the base case that we already saw in the pseudocode. And for each recursive call, right, we need to store, this is what I said, so we need to store some information in the stack, so where we called from. So that is v1, v2 and t in the stack. So when I say v1, v2, t, I mean from whichever state of the function we are calling from. So at maybe in some interim call, it will be some specific vertex, starting vertex, some specific ending vertex, and instead of this 2 power dfn, it may be some other value, right, in the stack, right? And each one of this v1, v2, t, right, v1 is a name of a vertex, right, and there are 2 power d times fn vertices. v2 is also the name of a vertex, and t is also 2 power dfn. And to store this v1 or v2 or t, we need a bit string of length log of that, right? So to store a number of size 100, we need a space of log 100, which is about 7, right? So if there are 1000 vertices, we need a bit string of length around 10, right? So if 2 power dfn vertices, we need log 2 power dfn. So log of 2 power something is simply d times fn, right? So this is simply dfn, right? D times fn, because log and 2 power cancel. And for this is what is required for each of the v1, v2 and t, and hence since this is what is required for each of v1, v2, t, the total space required is 3 times dfn, right, which is what we have here per recursive call, right? For each recursive call we need to save this, so total we need 3 times d times fn. And what is the number of levels? Again, the number of levels is what I said earlier, it is log t, it is the number of levels. Again, that is again another, log t is also d times fn. So the number of levels is also at most d times fn, right? Right. So the total space required is just the number of levels multiplied by the information stored at each level, right? So you have a stack, and at each level you need to store this much information, and multiplied by the space required to store each information. So space for one level of information multiplied by number of levels, it is 3 times d times fn multiplied by d times fn, which is simply d times fn squared. Maybe there is a 3 here, but it's still order fn squared. because d is a constant, 3 is a constant, so 3d squared times fn squared, which is still order fn squared. This is the total space required. And that's it, right? This is what we set out to prove. So we have a deterministic algorithm. So notice that it is a deterministic algorithm. Here, else for all vertices w is simply, there is no non-determinism here. We are just checking one by one w, right? And there is no non-determinism guessing going on here. And we have a machine that uses, a deterministic machine that uses order fn squared space. So we started with a non-deterministic machine that uses order fn space, and we are achieving the same computation by a deterministic machine that uses order fn squared space. And that's it. So that is the statement of the Savitch's theorem. Right? Deterministic, non-deterministic space fn machine, whatever it does can be accomplished by a deterministic space fn squared machine. Right? Okay. Now just one more comment. So now to actually do this, right, to actually devote space and make this call, etc., we need to know fn beforehand, right? Because otherwise this computation cannot happen, because the initial call has to be for t equal to 2 power d fn. So we need to know fn beforehand. What if we do not know fn beforehand? We can still do the same thing by simply trying out fn equal to 1, fn equal to 2, fn equal to 3, and so on. Just that we will eventually be successful in computation, in simulating the non-deterministic machine when we are at fn squared, which is the square of the space used by the non-deterministic Turing machine. So what I am saying is that if suppose we do not know how much space the non-deterministic Turing machine uses, and still we have to accomplish the simulation, we can still do that by simply trying out fn equal to 1, 2, 3, and so on, right? So what we can do is that the simulating machine can try out fn equal to 1, 2, 3, and so on till it finds a decision. So what it should try to do is the accept reachable when it is limited to fn equal to 1. If the accept is reachable, then you accept. If the accept is not reachable, now are we trying to move to configurations of bigger length? If we are not able to move to any bigger length configuration, then that means that even by trying out bigger space, we are not going to reach anywhere. So we accept if we reach the accepting state, we reject if we are not able to reach any bigger configurations, right? If accept is reachable, we accept, right? If no configuration of length of, let's say, of bigger length is reachable, we reject, right? Else we move to next value of fn. So just we continue the computation. This is what we can do. So again, this is a minor point that I said at the end, but the fact is that we can continue this, we can do this simulation even without knowing fn. That's how nice this construction is. So once again, what this shows is that I think there is some. What this shows is that yes, what which shows that whatever is accomplishable whatever is accomplished in non-deterministic space Fn machine can be accomplished in deterministic space Fn squared machine. So maybe you'll just write down one or two consequences and then stop. So consequences, maybe let's say d space, or sorry, n space of, or maybe I'll just write this, NL is contained in, NL is not deterministic space log n, it is contained in d space log square n. And maybe another result that I can say is n space n, again this is just something that I'm making up, is contained in d space n squared. So notice that whenever we have a polynomial expression in the left hand side, even the right hand side expression will be a polynomial one, because square of a polynomial is always a polynomial. N power k, if you square it, it's n power 2k. So in fact, if you consider something like NP space, right, which is the union of all n space n power k, just like we defined NP, right, k equal to 1 to infinity, right. Now this is contained in, now at each class here I could write d space of the square of the function, which is n power 2k, right, n power k, if you square you get n power 2k, but this is simply again contained in k equal to 1 to infinity d space. So we are just taking the union of all n squared, n power 4, n power 6 and so on. So we may as well take all integers, right, n power 1, n power 2, n power, that also contains all this. And this is, again, this I can call it p space. It's like a space analog of p, the class p, right. So what we have shown is that non-deterministic polynomial space is contained in polynomial space, deterministic polynomial space. So when I say contained in, the other direction containment is obvious, right. Deterministic polynomial space is always a is always a subclass of non-deterministic polynomial space. Now we have shown the reverse direction as well. So NP space is actually equal to P space. So this is also something surprising to us, right? Because in time complexity, NP is the biggest problem that we have. Right? Is P equal to NP? P is strict subclass of NP. But in case of space bounded complexity, then NP space and P space are the same, right? So today we saw the Savitch's theorem, which said that non-deterministic space Fn can be simulated by deterministic space Fn squared. So the proof using a recursive computation and some consequences, and that's all. Thank you.